Hi friends, welcome to somethingcalledscience.com, and today we'll talk about the naming rules for polyatomic ions. As you may know, there are different types of ions. Some of them are monoatomic, which means that they consist of only one ion. Remember, an ion is an atom that has a net electric charge. Other types of ions, however, are polyatomic, which means that they consist of two or more ions. These polyatomic ions carry a net electric charge as a group, and this is the type of ion that we'll talk about in this video. Specifically, we'll talk about the naming rules for polyatomic ions, because there are certain conventions for this. If you're interested in learning more about the difference between monoatomic and polyatomic ions, or about the naming rules for monoatomic ions specifically, we have separate videos about these topics. For now, let's focus on the naming rules for polyatomic ions. The naming rules for polyatomic ions differ for anions and cations. In other words, they are different for positively charged polyatomic ions, so for cations, and negatively charged polyatomic ions, so for anions. A net positive charge in polyatomic ions occurs because the number of protons, which are positively charged, is larger than the number of electrons, which are negatively charged. Hence, in this case, we have a cation. A net negative charge, on the other hand, occurs when the number of electrons is larger than the number of protons. In that case, we have an anion. Let's start with the naming rules for polyatomic cations. There are two conventions for naming in this case. The first is actually the least satisfying one because it is not very specific. This rule is that many polyatomic cations often simply do not have specific names that follow a strict naming convention. The naming in this case is primarily based on common names, which are unique and widely recognized in the field of chemistry. The names of these cations are often derived from their chemical composition or historical usage, and they are simply accepted as common names in the field of chemistry. The most well-known polyatomic cation is ammonium. Another example is hydronium. So this is the first naming convention for polyatomic cations, which is that in many cases naming is based on common names. However, there is one particular group of elements for which the polyatomic cations do have specific naming rules, and this is for the group of transition metals. So if you look at the periodic table of the elements, you'll see in the central block that there is a group of elements that is called transition metals, and they include, for example, iron, copper, and gold. What is crucial to grasp is that transition metals are distinct from other elements in a way that is significant for our topic. Namely, they possess the capability to display multiple oxidation states. In simpler terms, this means that they can lose varying amounts of electrons. In contrast, elements that are not transition metals do not have this flexibility. They can only lose a specific number of electrons. To briefly illustrate this, let's take the case of two monoatomic ions that are not transition metals, namely potassium and magnesium. Potassium can only lose one electron, forming a potassium ion, while magnesium, which isn't a transition metal either, can only lose two electrons, resulting in a magnesium ion. On the other hand, when we consider a transition metal like copper, we observe that it can lose different quantities of electrons. For copper, the most prevalent oxidation states occur when it loses either one or two electrons. Therefore, Cu plus and Cu2 plus represent the two main oxidation states of copper. So what implications does this have for answering our initial question, namely, what does this mean for the naming rules for polyatomic cations in this context? For cations derived from transition metals that can have multiple oxidation states, we use Roman numerals to indicate the oxidation state. For example, iron sulfate, where iron is followed by the Roman numerals for 2, indicates that iron has a +2 oxidation state. Iron sulfate, where iron is followed by the Roman numerals for 3, indicates that iron has a +3 oxidation state. In these examples, the Roman numeral in parentheses tells you the charge of the iron ion in the compound. So this is the second convention for naming polyatomic cations, which is to use Roman numerals in the case of transition metals. Let's summarize the naming rules for polyatomic cations. The first is to use specific names for common polyatomic cations, for example ammonium. And the second is to use Roman numerals for transition metals to indicate their oxidation state. These two conventions sum up the naming rules for polyatomic cations. Next, let's look at the naming rules for polyatomic anions. So, polyatomic anions are groups of at least 2 anions that as a group have a net negative charge. Like in the case of polyatomic cations, there are also conventions for how to name polyatomic anions. The first convention, and one of the most common ways to name polyatomic anions, is by using the suffixes ate and ite. These suffixes indicate the number of oxygen atoms present in the ion. Let's look at this a little bit more closely. Many polyatomic anions are part of a series or a group of related anions that share a common element, and so in that sense they are similar. What makes them different from each other is that they contain different numbers of oxygen atoms. In other words, they contain the same central atom, which is usually a nonmetal, but they vary in the number of oxygen atoms attached to it. So one anion may have more oxygen atoms than another, leading to different chemical properties. Now, this has consequences for how the polyatomic anion is named. Specifically, chemists use both suffixes and prefixes to distinguish between different polyatomic anions in the same series. First, let's take a look at the suffixes that chemists use for this. The specific suffixes that they use are ate and ite. And the rule here is that the polyatomic anion that has more oxygen atoms gets the suffix ate, whereas the anion with fewer oxygen atoms gets the suffix ite. As an example, consider nitrate and nitrite. Nitrate has 1 nitrogen atom and 3 oxygen atoms. Nitrite also has 1 nitrogen atom but 2 oxygen atoms. So between these two we see that the ion that has more oxygen atoms gets the suffix ate, and the one that has fewer oxygen atoms gets the suffix ite. So this is how chemists use suffixes to distinguish between different polyatomic anions in the same series, namely by assigning the suffix ate to the ion that has more oxygen atoms and assigning the suffix ite to the ion that has fewer oxygen atoms. Now, in addition to the ate and ite suffixes, chemists use a second way to distinguish between different polyatomic ions in the same series. Namely, not only do they use the suffixes ate and ite, but they also use prefixes. These prefixes are hypo and per. The prefix hypo means less than. It is used for the ion with 1 fewer oxygen atom than the ite form. For example, hypochlorite has 1 oxygen atom, which is 1 fewer than chloride. So the former gets the prefix hypo. In contrast, the prefix per means more than. It is used for the ion with 1 more oxygen atom than the ate form. For example, perchlorate has 1 more oxygen atom than chlorate. Thus the former gets the prefix per. So this is the second convention for naming polyatomic anions, namely that we assign the prefix hypo to the ion that has 1 fewer oxygen atom than the ite form, and we assign the prefix per to the ion that has 1 more oxygen atom than the ate form. Now, besides the naming rules for polyatomic anions that involve using the suffixes ite and ate and the prefixes hypo and per, there is one more naming rule for polyatomic anions. This third rule is that some polyatomic anions have unique names. Some examples are hydroxide, which is a common polyatomic anion, and cyanide, which is another polyatomic anion, often discussed for its toxicity. So this brings us to a summary of the naming rules for polyatomic anions. First, use ate for the ion with more oxygen atoms and use ite for the ion with fewer oxygen atoms. Second, use hypo for the ion that has one fewer oxygen atom than the ite form, and use per for the ion that has one more oxygen atom than the ate form. And third and final, some polyatomic ions have unique names, for example hydroxide or cyanide. In conclusion, we've covered a lot of ground. We've discussed the naming rules for polyatomic cations and for polyatomic anions. Let's recap what we've learned one more time. For polyatomic cations, we have two rules for naming them. The first is to use specific names for common polyatomic cations, for example ammonium. And the second is to use Roman numerals for transition metals to indicate their oxidation states. And for polyatomic anions, we have three rules for naming them. First, we use ate for the ion with more oxygen atoms, and we use ite for the ion with fewer oxygen atoms. Second, we use hypo for the ion that has one fewer oxygen atom than the ite form, and we use per for the ion that has one more oxygen atom than the ate form. And third and final, some polyatomic ions have unique names, for example hydroxide or cyanide. So there you have it. These are the naming rules for polyatomic ions of both types, cations and anions. If you found this video helpful, don't forget to like, subscribe and hit the notification bell for more science content. It really helps the channel out. Let us know in the comments if you have any questions or topics you'd like us to cover next. Thanks for watching and see you in the next video.